Hello, my name is Carl Cook, and I'm Chief Technical Officer of IntelliDynamics. And this is another in our series of technical presentations on capabilities of our Intellect product line. And today we're going to be talking about separating streams. What's that? Well, sometimes you have a number of, in engineering sense, unit operations. You have, let's say, Unit A and Unit B, and it's producing something, whether it's widgets or oil or whatever. And those units produce material, and they are that streams coming out of there are merged together and go over and are measured. And that measurement is, let's say, it's quite expensive. And you want to be able to measure your output from your units, and in the end you would like to know which unit is producing how much, but you only have one measure. And so you might start Unit A and then start Unit B and shut down Unit A and whatnot, and take your measurements, and you'll get a little chart like you see below, where you have measure versus time, and from that you can deduce what Unit A and Unit B are producing. And that doesn't take very much magic. You just kind of take the differences in the levels depending on which unit is operating. And since we have two units, we have 2 to the 2 possible operating states. So 4 possible combinations, and so the chart that I've shown there has 4 levels. However, life is not that simple. It's just, you wish it was, but it's not. Well, let's say that you've got 10 units, and now you've got all sorts of different levels as you start and stop various unit operations. Now you could shut them all down and just run one unit, and then shut that one down and run a different unit, and shut that one down and run a different unit. But you're trying to produce product, so by shutting down all units but one, you're actually deferring or reducing your output and utilization of your facility. So you don't want to do that. So you have various units normally operating as they do day to day, and they're starting and stopping, and you end up with 10 units. You might end up with a chart that's down below there where you have all sorts of different levels. And with 10 units, you have 2 to the 10th possible on-off states, or 1,024 possible combinations. And then if that goes to 11 units, then it's, it grows rapidly. And but life isn't that simple. It never is. Because your measurement may be quite noisy. And in the chart I show down below, depending on, in the sample example, I know what the production is of each of the units are. And I know that, just by setting up this challenge, I know what the noise is, because I've synthesized some data I'll show you, or in that chart down below, and I know that actually the noise that I'm injecting, depending on the unit, is between 50% error, that's quite a lot, and 500% error, and that's huge. So so now we have 1,024 possible combinations with noisy measurement. And so our little measuring guy there is he's getting a little upset, because how is he supposed to figure out what's coming from each unit based on only one measurement device? But it is possible. And another challenge might be that each of these units might interfere with each other. So by operating Unit 1, it may actually suppress the ability of the Unit 2, because they are on the same conveyor or same pipe or same whatever. They might interfere with each other. So by turning on Unit 2, you might actually, reduce the output of Unit 1. Well, okay, now we've got a challenge, and this is very much like real life. So, what do? First of all, we model the situation using technology which learns the states of n units versus the measure, and so that we can tunnel through the noise and take the noise out. So the blue line is the synthetic data, and the red line is the model outputs. Oh, okay, so all of a sudden now we've taken the noise back out of that using superior nonlinear predictive modeling technology that learns the relationships of units operating, each unit operating versus the output. And we've eliminated the noise, and we can also, with this technology, we're able to accommodate for the nonlinear interactions between units, because the modeling technology is looking at all units simultaneously and whether or not they're operating and whether or not they're interfering with each other. Then once we have that model, we can turn states on and off in that model to get combinations of states of interest. So for example, given units 3, 9, and 10 are operating, what's unit 5's output? Because 3, 9, and 10 may interfere or enhance or reduce the output of unit 5. And so we go through and take a look at these combinatorial states of interest, measuring the output, and we turn on and off, say, unit 5's. We turn on 3, 9, and 10, and then we turn on and off unit 5 and see what is the difference in the output of the system, which gives us an indication of what unit 5's output is in that particular operating situation. And then we can, for all units that operated during the time of interest, such as through that trend chart that I showed, we can deduce what each unit's rate is from the noisy data. So I know in the synthesized data that unit 1 actually produced 1 unit per unit time. Let's say 1 unit per hour. Unit 2 produced 2. Unit 3 produced 3. Unit 4 produces 4, etc., up to unit 10 producing 10 units per hour. And so by using this modeling and combinatorial turning on and off of states, the system determined that unit 1 was about 1.2, unit 2 was 2.1, unit 3 was 2.9, or basically 3, unit 4 was 3.9, or basically 4. And so you can see that the system actually figured out for all units, except for the one that did not operate, because that data set was set up such that unit 10 would never operate. It determined what the actual rate was within a reasonable error. Now in the beginning we had 50 to 500% error. 500% error means that unit 1's production was injected with as much as 5 times the unit rate error, and the system still figured out that it was about 1.2. So the resulting error in the determinations are about 10 to 20%, given the data set that was processed. And we have a reasonably good determination of which each unit actually produces. Now there's some caveats to this. First, you need a reasonable number of state changes. You should probably at least have 1 state change per unit that you're going to analyze. Like unit 10, it didn't have a state change, so we couldn't really analyze what it was going to be. But the other units did have state changes. And in that data, we had about 12 state changes out of a possible 1,024 states that the system could be in. I mean, we still did quite a good job. That's 12 out of 1,024. That's a pretty small percentage of possible states that we analyzed and came up with very close answers. But we need at least 1 per unit, but we don't need anywhere near the total number of permutations. It's just not necessary. And we need sufficient measurements at each operating state to be able to negate or neutralize the noise. So we need to be able to tunnel through the noise. If you only took 1 measure at each state and there was a 500% noise injected in there, you might just happen to hit a number that was high or just happen to hit a number that was low. And so you need sufficient measurements to at least so the system in the modeling can compensate and identify what that noise contribution is. And we can make reasonable guesses at unknown combinations of states that we've never seen, but we have to be cautious of that. If there are interactions, then it's possible that we may not be quite as accurate. If there are not interactions, then we're probably good. So, what did we achieve? We didn't have to measure each unit's output, and if that measurement is quite expensive, instead of having one measurement, let's say at $1 million for that measurement, we didn't have to spend $10 million. We could just use that one measurement. So we didn't have to measure each unit's output. And we determined each unit's output from something that was quite messy and only using 12 state changes, not 1024. We did not interfere with any operations. In other words, we didn't have to shut down all units and run one of them, and then shut down all units and run a different one, or to divert the production over to some other location. We reduced the error from 50 to 500% down to 10 or 20. That's pretty good. And with some more data, we could probably get that even lower. More states than 12, longer durations at each state. We could probably get that down much lower yet. The model that was developed of those combinatorial states can be put online to validate the measurement. And we have done this before, where we have taken state measurement models like this and put them online, and they hold up out of sample, which means that the model is good. And you'll note that the solution can handle any number of units. You have to mine the data, but you'll need more with more units. But there's no physical limit to the number of units. The more you get, the more states you need, the longer maybe durations to quantify the noise. But there's no restriction on the number of units. So whether it's just 2 or 10 or 20, it doesn't much matter. So anyway, I appreciate your time. Thank you very much. I hope this helps you understand using some nonlinear magical technologies to separate streams of many different units with lots of noise going through only one measurement station to quantify that. And hope that you find this useful. Thank you.